This is the lecture 6 of our computational microelectronics course. Due to my another business trip to San Jose in this time, so I have to record this lecture 6. So thank you for your kind understanding. So then now let's go to lecture 6. Today we'll talk about how can we implement one-dimensional source-free Poisson equation. So this is the very first time to consider real space discretization. Up to now we have thought about MOS capacitor. So MOS capacitor was taken as just a silicon region or the region covered by oxide. Of course, real MOS both contains O and semiconductor. So the second description is the correct one. But anyway, we considered a semi-infinite silicon sample starting from x equal to 0 and extended up to x equal to infinity. And we assume homogeneity in this deep substrate, and something happens only nearby x equal to 0 point. Well, anyway, when we consider such kind of a system uh, with a uniform doping concentration, for example, Na something, then we were able to get an analytic expression for the surface electric field. So this quantity is the gradient of electrostatic potential evaluated at position x equal to 0. Since this x equal to 0 is the interface between oxide and semiconductor, and also this d phi over dx is closely related to the x directional component of our electric field. So this quantity can be regarded as just a surface electric field. So the square of a surface electric field is well expressed as certain quantities already known to us. For example, universal constant and given temperature and material dependent constant, and also at a given temperature we know intrinsic carrier density. Also depending on doping concentration, yes, we know the potential at the substrate, and the only thing we wanted to know in this case was this surface potential, not surface field, but surface potential was the only thing we wanted to know. So here we have also surface potential, and surface potential. It means that once we know the surface potential, then we can calculate surface electric field. In other words, if we know surface electric field, then by applying the Newton method, then we can calculate surface potential. Even when we have oxide layer whose thickness is T ox, still we can do it. And when we have a certain gate voltage, then it is converted into, for example, um, into the electrostatic potential by the way of Vz minus flat band voltage. And with this quantity as a boundary value at this gate side, and also with this value as the boundary condition at deep substrate and positive infinite, then we were able to calculate this surface potential which is defined as the surface potential minus the potential at deep substrate. Yes, we were able to calculate this quantity numerically. So that was significant achievement. However, it was a rare case. We can make this problem much more difficult by introducing additional conditions. What is the additional conditions considered in this case? For example, instead of this homogeneous doping concentration, for example, if we have some position dependent quantities like this way, then what will happen? Or that way, then what will happen? So in this case, the simple expression for this surface electric field will not be able any longer because previously we have made the fact that the doping concentration is constant all over our semi-infinite semiconductor region. Okay, so yes, so by introducing such kind of a little bit modification, we can make it much more difficult. So therefore, we need a general way to solve a general equation. So not restricted by some constantness of doping concentration or simplicity or symmetry of our geometry, but instead of that, we wanted to solve any problem, although we must provide certain computational effort. However, we wanted to make a general way. So that will be discussed in today's lecture. Okay, so first of all, we have to understand the integration is the one, the global integration was the key for simplification. For example, we performed in previous case something like this one. Yes, our certain function was integrated with respect to this mm, electrostatic potential reference to the deep substrate. So this value is corresponding to the position equal to x equal to 0. And of course, this 0 value for phi bar is corresponding to x equal to infinity, the deep substrate. So by performing this kind of integration, previously we had certain complicated expressions, but that can be just merged into one single expression. So internal distribution of a quantity can be simplified and expressed as a single scalar. That's good. However, please have a look at these two examples. So now let's assume that these two graphs just shows two different distributions of a certain quantity. For example, yes, for example, let's say that this is electron density, for example. Yes, this is electron density. When this is electron density, well, when we just make an integration, then we are more or less interested with this area underneath these two blue boxes. And of course, they have the same area. So simply speaking, if we make such kind of n, then these two different distributions will give us the same value, same scalar value. However, that does not mean that this distribution and this distribution, two different distributions are identical. of course, they are quite much different. For example, instead of this simple number of electrons, but if we wanted to uh, consider just the average distance of electrons from this 0 point, then how does it look like? For example, yes, in this case, if we consider uh, for example, average distance, then maybe we'll say that okay, maybe electrons average distance is located here because this is a negative part and positive part, and we will just consider absolute distance. So maybe electrons will be centered at this half position. Then how about this condition? Of course, in this case, if we ask ourselves the average absolute distance of this electron distribution, then we'll say that, okay, the electrons are centered at this point because they are more widely distributed compared with this left side one. So simply speaking, although two different distribution can give us um, two identical or sometimes identical result, but it does not necessarily mean that these two distributions are really identical. So they can be different. And of course, by performing this integration, we are doing certain simplification and certain information is lost, and in this case the distance information is lost by performing this integration. Okay, so although integration is really a powerful tool for simplification, but uh, it is not uh, it does not keep all the information. So the better way is not doing this integration over all over our system, but we need to keep the point-wise information. So instead of considering an equation entirely integrated over our entire domain, but we wanted to have a certain description of an equation only integrated over small domain, relatively short distance of our entire domain. So that will be done in our today's lecture. Okay, so let's go to this case. Let's assume that our entire simulation domain is made of L1 from L1 to L2. For example, it can be, for example, minus 100 nanometer and say that 10 micrometer, whatever, or this number can be, for example, 10 micrometer, and this can be 20 micrometer, whatever. So we can consider just a general pair of L1 and L2. Of course, L2 should be larger than L1. Then we can introduce a finite number of points to describe this one-dimensional domain. So the left-hand side or left boundary is L1 and right boundary is L2, and we can, for example, introduce n points here. There, 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 there. Okay, so we can, for example, in this case, we have introduced 7 different points, and up to now, the only restriction is, okay, its first one should be corresponding to L1, and its last one, in this example, seventh one, should be corresponding to the L2. And if we uh, arrange our point in that way, then this is generally non-uniform. The distance between two neighboring points are not the same. So, for example, here we have a short distance, and here we have a relatively long distance. So, in this case, we call it as a non-uniform form grid. However, for our simple notation, we will just consider a uniform grid. It means that instead of this non-uniform or non-uniform placement of a point, so we will just consider equidistance points here and there. 1, 2, 3, 4, 5, 6, 7, and let's assume that their distance, the all of these distances are the same. Then we can say that this is a uniform grid. And how can you find the position? Here it is quite easy. Starting from L1, the distance between two neighboring points can be multiplied by the number. For example, if we start from I equal to 0 and ends up number 6, so the first point is called or indexed as the zeroth point, and the last one, the seventh one, is indexed with the number 6, so 0 based indexing is applied. Okay, so in this case, we can just simply write down in this way, starting from the initial point and equidistance and number of uh, steps. So for example, when we have I equal to 0, and this is very first point, so this one doesn't contribute, and we will just recover this L1. And if we have the last point corresponding to n minus 1, then, in this case, this product will give us unity, and sum of these two numbers will give us just L2. So we can easily understand this expression correctly makes some points uniformly distributed all over our simulation domain. Then, once we introduce several points, then we introduce also unknown variables defined at those points. So, for example, in this 7 points example, then we also introduce 7 unknown variables corresponding 7 points. For example, here phi evaluated at x0, and here we wanted to define phi evaluated at x1, another one phi evaluated at x2, and finally, yes, phi evaluated at x sub 6. By introducing these electrostatic potential values evaluated at all discretized points. So now we have a vector of these electrostatic potentials. So instead of finding now our electrostatic potential everywhere inside our domain, so that is the analytic solution, but instead we try to find a solution vector. So this does not include the infinite number of unknown variables, but only n multiple uh, unknown variables. So information is much smaller than the analytic one, and which satisfies an appropriate equation or the boundary condition at those discretized points. So it means that um, by introducing this discretized point, and when all of these unknown variables defined at discretized points satisfy these discretized equation, then we are happy within this numerical analysis. Of course, I wanted to say that is this perfect. So in this sense, we just calculate on approximate solution about this problem. The original problem is not fully solved by this insufficient information, but that is our assumption. Although we must find out all electrostatic potential at any x value, instead of that, we are happy with just small fractional information. Yes, once we know only these 7 numbers, then we will say that, okay, we have done it. We have got the solution of this problem. Okay, there is a significant difference between this analytic solution and discretized solution, but that is our belief. So we wanted to believe that this is a good approximation about the real analytic solution. So when this concept was first introduced several decades ago, so there was a serious discussion between some old school guys and new numerical analysts. So, however, nowadays it is regarded as just okay to treat this problem with this discretized manner. But I wanted to emphasize that this is just an approximation. So we always, by performing this numerical analysis, we get the approximate solution about the original problem. So don't be overemphasize or overestimate the solution we get out of this numerical analysis. Well, anyway, so please keep in mind this one. Then today we will try to solve Poisson equation, but not the general Poisson equation, but we will try to solve a simplified, special version of a Poisson equation. So then what is the Poisson equation? Poisson equation is actually the mathematical term for representing a certain set of equations, certain class of equation. However, in this lecture, when you say Poisson equation, it is actually the Gauss law. So the Gauss law is shown here. It simply means that the net charge density law is the source of the displacement vector dr. This is the meaning of our Gauss law. Yes, so when we have a net charge density, then it will generate a displacement vector, and this displacement vector is closely related to the electric field inside the simple material. So we have a simple scalar value here, permittivity. So yes, so with okay, so I made a mistake. Gauss Okay, so anyway, simply speaking, when we have a net charge, then it will generate the electric field that is described by the Gauss law. Yes, so this is the form frequently used in our textbook. However, under the electrostatic assumption, so we can now write down the electric field in terms of electrostatic potential. So simply D is expressed by permittivity times electric field, and this E, electric field, is represented as gradient of electrostatic potential. So when we just insert it into our original function here, then now we have a little bit modified term, and now you can identify there occurs some partial derivative with respect to the real space once and twice. This is corresponding to the second order derivative with respect to the real space position. So this is the form of a frequently used Poisson equation. However, when the permittivity is a constant, then now we can just pull out this generally position dependent permittivity in front of this derivative. So now we can make a simplified form as shown here. So only in this form we can write down in this way. So the Laplacian of our electrostatic potential is given as a certain position dependent function, so minus rho over permittivity, and this is generally non-zero. When we have such a form, so uh, Laplacian of a certain function is non-zero and given as a certain source function, then this form is called as Poisson equation. So that's the reason why this Gauss law is called as the Poisson equation in our context. However, more generally adopted form is shown here, which allows a position-dependent permittivity. So in a rigorous sense, our equation, our Gauss law is no longer identical to the Poisson equation, but that is a long historic convention to name it as the Poisson equation. So we will just follow that convention. And we can make it even further simplification. So if we don't have any net charge, so net charge density vanishes. In this case, we can have this form, and this form is of course called as Laplace equation. Okay, so that's the reason why when we have a net charge when we have zero net charge density and homogeneous material where the permittivity is constant, then the Poisson equation can be reduced to the Laplace equation. However, in today's lecture, we will not consider a Laplace equation. Instead of that, we will just keep this position-dependent permittivity. Instead, we will just say that, yes, net charge density vanishes. So in that case, today's main equation, source-free Poisson equation can be obtained. Okay, here we have 0, which is originated from 0 net charge density. And here we still keep the position dependency of permittivity. Okay, so let's move on. Then, how can we make such kind of a discretization for this operator. This operator is just left-hand side term of our source-free Poisson equation. So let's just do it. Since we will restrict ourselves to only to 1D, so first of all, it becomes more easier to write down this gradient operator, del operator, as d over dx. So in 1D, this is quite much acceptable. Then how can we further discretize this expression or this operator? So what we can do is make an integration once again, but not from L1 to L2. If we do it, if we just integrate our equation all over our entire simulation domain, then every information is just lost and we will have only a single scalar value. However, instead of that, we restrict the domain of integration around a short distance nearby at a certain position, xi. What is xi? I can be 0, or I can be 1, I can be 2, and I can be even n minus 1. You can select any of these available n candidate for I value, and you can do it. So when we make such kind of a selection for xi, then from xi minus half to xi plus half means that we wanted to make an integration from the midpoint between x and x minus 1 and another midpoint between x and xi plus 1. So this point is here denoted as minus half point, and here we have a positive half point. We will just make an integration over this range. So when you do it, then we can make much simplified expression. So let's do it together. So of course, this expression itself is a differential form. So when we make an integration and this first derivative can be eliminated, and of course we must evaluate the internal form at lower bound and upper bound. So by performing this integration, we have to calculate the permittivity at upper point and this first derivative at upper point minus permittivity at lower point and d phi over dx at lower point. We should evaluate this one. But anyway, how can we make a discretized form of this seemingly complicated expression? The answer is just to make another integration over short distance. That is my answer. Then question is, can we take this epsilon at this midpoint, and can we take epsilon at this midpoint without any ambiguity? Yes, we can. For example, let's just think about this domain. Let's just say here and here we have material 1 and material 2, and let's introduce a certain point here. Of course, we will have a point here and point here and point here. Important one is at a material boundary, we have also a point. So at this material, maybe it would be quite difficult to define whether this point is really belonging to material 1 or material 2. So if we ask, for example, let's say that this is corresponding to x sub 11, then if we ask ourselves, what is epsilon at x sub 11? So it would be quite difficult because that is exactly located at the boundary points. However, for example, if we ask ourselves what is permittivity over x sub 10 or what is permittivity over x sub 12, then it is easy to answer because this point is certainly belonging to M1 material, and this X sub 12 is certainly belonging to M2 material. So now our question is, how about this midpoint? Isn't it midpoint is ambiguous or not? Mhm. So midpoints, for example, they are located here and there, and quite fortunately, since this is there is no chance for this midpoint is belonging to the interface, so it is always either M1 or M2. So we can decide its permittivity and that permittivity without any ambiguity. Okay, great. And the remaining task is just to approximate this first order derivative of electrostatic potential with respect to the position at these two midpoints. But that can be done quite easily. So let me just show it to you here. Yes, how can we make a discretization of this d phi over dx? So the position is, the coordinate is like this. Here we have a discretized point called as x sub I and another one x sub I plus 1. And of course we have phi evaluated at that point, and sometimes it is noted as phi sub I. And here we have a phi evaluated at x sub I plus 1, and it is denoted as phi I plus 1. Yes, we know these two quantities, but right now we have no idea about the phi over dx evaluated at this midpoint. So uh, x sub I plus half is corresponding to this midpoint. So we don't have any well-defined potential values. And yeah, right now we have no idea about its first gradient. But in this case, we just take the linear approximation. Within this short distance between x sub I and x sub I plus 1, we just have linear dependence, linearly varying potential function. So then what will be this first order derivative? It becomes really easy to say because we have to consider the difference between function, which is divided by the distance, xi plus 1 xi. So that is shown here. So simply speaking, our ultimate goal is to discretize the left-hand side term of our one-dimensional source-free Poisson equation. And by taking the integration of a short distance, now we have the first order derivative evaluated at upper bound and lower bound, and these two first order derivative can be well approximated with this linear approximation. So when we combine them, then the left-hand side term, which is integrated one, now simply becomes in this way. Wow. So now let me just give you a concrete and concrete expression. For example, let's say that ix plus 1 and xi equal to delta x, and also that is the distance between x sub I and x sub I plus 1. So it means that we have a uniform grid with a distance of delta x. Then this one just simply given as, also let's say that this is epsilon is constant. In the case, now we have epsilon delta x phi I plus 1 minus phi I minus epsilon phi I minus phi I minus 1 delta x. So let me try to consider the coefficient for phi I plus 1. How large is it? Its coefficient is simply given by permittivity divided by delta x. Then my another question is, how about the coefficient for phi sub I? In this case, we will have minus epsilon delta x originated from this first term, and another one originated from the second term, yes, minus epsilon over delta x. So we will have 2 times epsilon delta x. And finally, the coefficient for phi sub I minus 1, that is also the same as delta epsilon divided by delta x. Okay, now we can consider the coefficient for these unknown variables. Of course, when we have different values, epsilon and epsilon, then of course we can introduce different notations for this first epsilon and second epsilon. Then, for example, let's say epsilon 1, epsilon 2, then we will have epsilon 1, 1, 2, 2, 2. That will be the result of this discretization. So now, up to now, we have discussed about the way to discretize our left-hand side. So simply speaking, second order derivative of electrostatic potential when the permittivity is position dependent. So let's consider a simple one-dimensional example. Consider a capacitor with 2 layers. So one is 2.5 nanometer thick, and another one is also 2 nanometer thick, and epsilon is here, relative one is 11.7, and another one is corresponding to 3.9. Everybody understand in this classroom should understand this is corresponding to the relative permittivity of silicon, and this is corresponding to the relative permittivity of silicon dioxide. So anyway, now we have silicon and silicon dioxide, but silicon usually have carriers. However, we will just treat this first layer also as a dielectric layer. There is no carrier at all, so we just treat it as a dielectric material. And now we have a potential at this point 0 volt, and this point 1 volt, and by solving the one-dimensional source-free Poisson equation, please try to calculate the potential all over our domain starting from 0 and ending at 5 nanometer. So let's go to this case. Of course, we can make the problem much more difficult, but uh, let me just consider uh, n equal to 5 points. It means that now we have x0, x1, x2, x3, and x4. And x0 is corresponding to 0. And this is corresponding to number 5 nanometer. And here we have 1.25 nanometer and 2.5 nanometer and 3.75 nanometer. And since we have two different layers, so the boundary between these two different layers is located at x equal to x sub 2. So as shown here, at x sub 2, the middle point, two layers, so silicon layer and oxide layer, are meeting together. So this, this everybody can understand this point will be quite special. So now let's try to collect equations at x sub 1, x sub 2, and x sub 3. Why we don't care about x sub 0 and x sub 4? These 2 points are corresponding to L1 and L2, two leftmost point or rightmost point. So for these 2 points, instead of applying the source-free Poisson equation, we just introduce the boundary condition. Please have a look at this first law and the last law. So let me just evaluate this first law. So here we have all 0 except for this one. And here we have a solution vector. The matrix multiplication can be done by just taking the multiplication of these two entries and multiplication of these two entries and these two, and these two, and summing them all. So what will happen if we perform this kind of a matrix operation, matrix vector multiplication? Then this first law will be just phi evaluated at x sub 0. So that will be the first law of a resultant vector. And it is equated with this number 0. What does it mean? It means that here we have applied this boundary condition for x equal to 0 nanometer. Then let's visit the last law once again. Here we have 0, 0, 0, 0, 1, and when we make a multiplication, we have to perform multiplication of these two numbers, multiplication of these two numbers. Yes, yes. However, all of these four multiplication will give us just number 0 because one of them is always 0. And finally, when we take this operation 1 and phi, then we will have phi at x sub 4 equal to number 1. What is it? This is once again corresponding to our another boundary condition evaluated at the rightmost value of position, so right boundary. So now you can easily understand just following this matrix vector multiplication. Now we can recover two boundary conditions evaluated at x sub 0 and x sub 4. Then let me just consider this second line corresponding to x sub 1. Then that is simply, let me just write down here, epsilon 1 times phi 0. minus 2 times epsilon 1 times phi 1 plus epsilon 1 times phi 2, that is corresponding to number 0. It is just second line, second row of our left hand side term. Then what is it? Actually, we have to show this discretized form of our Poisson equation. Then is it related with this form? So let me just do it together with you. So this is nothing but if we just multiply delta x and everything is just divided by delta x, non-zero positive value, then epsilon 1 delta x phi 2 minus 2 times epsilon 1 delta x phi 1 plus epsilon 1 over delta x phi 0. Yes, what is it? It is nothing but the integrated second order derivative when permittivity is identical between material 1 and material 2. Yes, so no, of course this delta x is a positive number, so multiplying this positive number to the left and right side or not doesn't make any difference, so this is corresponding to this equation. So now you can understand this second row is corresponding to the discretized version of our uh, source-free Poisson equation, and please try to check it this third row. So note that the third row has a different coefficient. Here we have epsilon 1, and epsilon 1, and here we have epsilon 2, epsilon 2, epsilon 2. It is because this one is corresponding to the material 2 and this one is for material 1. However, x2, this is the middle point and the boundary point between material 1 and material 2, and in this case we have a little bit different coefficient, and that was already covered in our discussion in this derivation. Okay, so now let's go to this form. So now you understand, although at first glance it sounds a little bit strange, but this matrix vector multiplication form just to describe the collected version of 5 equations. So please, here we have a form like a x equal to b. Here a is 5 by 5 matrix or square matrix, and here x is 5 times 1 vector, and also b is 5 times 1 vector. What is b? This is b. What is x? Our unknown vector is corresponding to the x. And what is the A? This 5 by 5 matrix is corresponding to A. So now we have this form, and this form can be regarded as a collection of equations evaluated at x1, x2, and x3. Also, these equations were augmented with boundary conditions, which were evaluated at x sub 0 and x sub 4. So simply speaking, although this is written in a form of a matrix vector multiplication, but its physical meaning is just a collection of our one-dimensional Poisson equations evaluated at discretized uh, grid points. So by solving this equation, then we will get the unknown variable which satisfy our Poisson equation at every point inside our domain. So that is the key. Of course, the actual implementation, when you try to actually implement this one, first of all, you have to construct a matrix corresponding to this guy, and also you have to implement the b vector here, and after that you must use a certain library to solve ax equal to b problem. So this ax equal to b, that is so frequently appearing in the numerical analysis, so usually we have a specialized routine to solve this expression or this matrix equation. So you don't have to actually uh, develop it. So just to provide A matrix and B matrix, and you will get the solution X out of the action of your library. Or in principle, you can do it by yourself. For example, if you can calculate the inverse matrix of A, then just to multiply inverse matrix, then you will get inverse matrix A times B. But calculation of this inverse of A is quite heavy, numerically heavy. So instead of that, so our specialized numerical solution just to calculate this unknown variable or unknown vector x without fully calculating the entire inverse matrix inverse of A. But that is just a matter of numerical calculation, and so we will not dive into that topic too much. So anyway, by solving this system for n equal to 11 case, then you will have this relation. So these dots just shows discretized points. Okay, now you have 11 discretized points, so you have 11 dots here. And as you can see, up to 2.5 corresponding to the silicon, you have a relatively slow slope or lower slope, not very steep. But in this point corresponding to the oxide, so now you find that the slope becomes steeper. Why does it happen? Because at this point, your two different materials meet together. However, the important one is not matching the slope itself, but we have to match this quantity. So epsilon times d phi over dx should be matched between two different layers, and since it has much higher permittivity, and since it has much lower permittivity, simply means that yes, this is corresponding to the steeper part, 3 times steeper gradient in this second layer. Okay, so then now let's go to our homework number 6. So due to my business trip, so due of this homework number 6 is quite much postponed. Okay, so also we have the temporal public holiday in this year. October 1st was announced as a public holiday this year. So we don't have any lecture October 1st and October 3rd. This is a national holiday also. So your due date is postponed to the October 8th. And in this case, The problem is quite simple. Just to solve source-free Poisson equation, just we did in this example, but instead of this 2.5 and 2.5 case, now we have just 1 nanometer thick oxide layer and 2.5 thick silicon layer. Okay, so now the boundary value is now 1.7 volt, and here we have minus 0.5 volt. But anyway, you can make it quite easily. So if your number is 1.7 and minus 0.5, then you can just change your these two values corresponding to your newly introduced boundary values for leftmost point and rightmost point. You can do it. And another point is now your midpoint is no longer placed at the center of your device. So you have to keep where is the point for changing the permittivity. Yes, in your homework problem, you have to keep it that in mind. So anyway, by introducing that one, if you do it correctly, then of course you will get the changing of slopes in here and there. Of course, here you have a steeper one, and here you have a relatively moderate one. So the problem is, yes, draw the potential, and of course this problem can be solved also analytically. So please make the simple comparison between your numerical solution and the analytic solution, and you can get some confidence on the correctness of your solution. Okay, that was all for our homework, our lecture number 6. So I hope that it was helpful to you. So that was the lecture 6 was the first time to be exposed to the discretization of a real space. However, in my opinion, there is not that much more complicated technique in this course. In this semester, in my opinion, actually, if you can understand this discretization procedure, then this is more than okay to attend this year's this semester's computational microelectronics course. At least this device simulation is involved. So today's lecture is particularly important. So please make your own effort to solve this homework number 6 by your own course. Okay, so well, that's it. Thank you for your attention, and see you once again October 8th in offline. Thank you.